So the normal distribution, and we've got our table of values for the standard normal distribution. We don't have a table of values for every normal distribution. So the question is, how do we turn a normal distribution into a standard normal distribution? And then we can use the tables and look up the values. So our random variable z, that's what we want. We want the standard normal distribution, and we know it has this particular formula for its density function. Let's play with it. If I was to substitute in z on sigma, if we think back to when we were dilating graphs, that's going to stretch the graph horizontally by a factor of sigma. And the formula would become this. I'd replace z with z on sigma. Remember, we want the area under the curve to be 1. But if I dilate it, it's going to change the area, and it'll increase it by a factor of sigma, the dilation factor. But I want it to be 1. Well, rather than think about that weird shape, let's think of it as a rectangle. So what I'm saying is we're beginning with this rectangle, base times height. We want that to be 1. And at this stage, it is 1. But I'm going to dilate it. So I would like that area to be 1, but it's not. It's now sigma. So how do I get it back to being 1? Well, now I need to stretch it vertically, because I've stretched it horizontally, but if I now stretch it vertically with another dilation, then I can get the area the way I want it to be. So if I now stretch it vertically by a factor of 1 on, you see that, oh look, the sigmas cancel, we get it back to an area of 1. Okay, so now that new one I'm going to stretch by a factor of 1 on sigma. So what would that look like? It would now become this. I'm multiplying it by 1 on sigma. So it'll become 1 on sigma root 2 pi e to the minus z squared on 2 sigma squared. Okay. But the other thing I want is I want to move the average, because I want the average to be 0, and it's not always going to be 0. So I need to shift the whole thing horizontally to get that center to be at 0. So if I subtract mu, it's going to shift it right, mu units, whatever the average is. That then gets this formula. Well, hang on. That is the normal distribution. So these two distributions now become equivalent. Right? Just through a series of dilations and stretches, I can show that they are equivalent if I make this substitution. Hence, this explains where your z-scores come from. You want to work out a z-score, you subtract the average, you divide it by the deviation, and it brings your score back to the normal distribution. So that's the substitution we can use. So z-scores, every normal distribution can be changed to the standard one using that standardisation equation. So our new random variable z will be the old random variable x minus the average divided by the deviation. As we know, that's what we call the z-score. A z-score represents how many deviations a score is above or below the average, and you usually give a z-score to 2 decimal places. So what does this mean for things like quartiles and these things called outliers? Quartiles, well, Q3 we know is 75% of the data. So our cumulative, so capital phi there, our cumulative Q3 would be 0.75, that's what we're saying. If we look that up in our tables then, it's 0.6745. By symmetry then, Q1 must be minus 0.67. The interquartile range then becomes 1.35. Why is that important? Because our definition for an outlier will always be 1.5 times the interquartile range away from the quartile. So Q3 or Q1 in the other direction. That's how we pick up outliers. So for a standard normal distribution, if your z-score is more than 2.7 or less than minus 2.7, then you would be considered an outlier in the data. And if you're investigating the data, then you make a decision. Am I going to include this piece of data or not? Because if you include an outlier, that can have an effect, obviously, on the average and things like that, and doesn't give you a true representation of the data. So any outlier, absolute value of the z-score, greater than 2.7 deviations of the mean. So you might now want to go back through your test reports and go, hang on, am I more than 2.7 on any of these? So the time spent waiting for a prescription to be prepared at a pharmacy, which can be annoying sometimes, is normally distributed, average waiting time 15 minutes and deviation of 2.8 minutes. So what's the probability that the waiting time is going to be more than 20 minutes? Okay, you go into the chemist, you want to know, oh geez, I don't want to wait more than 20 minutes. So what's the chance we're going to wait more than 20 minutes? So my random variable, I'm going to call it W for waiting time. So it's going to represent the waiting time in minutes. It's normally distributed, they've told me, and the two pieces of information I want is the average and the variation, 7.84. I don't write 2.8 there. Remember, you write the variation there, not the deviation. So 7.84. We now know I can get this to a normal distribution. So asking for W being greater than 20 would be equivalent to asking Z is greater than 20 minus 15 divided by 2.8, which is 25 on 14. Look that up in our tables. We get 0.96293, so 0.03, roughly about a 4% chance that we'd be waiting more than 20 minutes. The TQ company, what could that stand for? TQ, anyway. They make soft drinks sold in 330 milliliter cans. The actual volume of drink won't always be exactly 330 because you just got a machine that's putting in. They're pretty good, these machines, but they're not always going to get 330 mils each time. So they've found that it's distributed normally, they know that, and the deviation is 2.5 millilitres. But they want to ensure that at least 99% of the cans will end up containing more than 330. They don't want to rip their customers off. So they want to get a really good chance that they're going to get more than 330. So how much should they set their machine on? How much do they, I want you to deliver this much into the can. So they're not going to set it at 330. They're going to set it at more than 330 to try and get 99% of it being more than 330. V is going to be our volume of drink. So volume is normally distributed. It's the average we're trying to find because that is what we're going to set the machine at. The variance is 6.25. We want to know when is V greater than 330, which would be equivalent to finding when is Z greater than 330 minus this average, this number we're trying to find, divided by 2.5. So we're saying that cumulative one has to equal 0.01. We want greater than to be 99%, so less than would be 1, and that's what we look up in our tables, is the less than. So we only want 1% less than that amount. If we read from our tables what gives us an answer of 0.01, we can find that it's negative 2.33 would be the number that we'd be looking for. So we know this is negative 2.33. Playing around with it, we get that average needs to be 335.825. So if we set it at 336 millilitres, then yeah, we got a pretty good chance there that 99% of these cans we produce will have the correct volume or more. Biologists, they love playing with data, biologists. Collecting data on the heights of particular species of cactus. This is something we would like to know. They observed that 34.2% of the cacti are below 12 centimetres in height. 18.4% are above 16 centimetres in height. Now, we have to make the assumption that heights are going to be normally distributed, but let's find the mean and the deviation of this distribution. So H is going to be the height of the cactus. It's normally distributed, but this time we don't know either. What is the mean? What is the variance? They've told us that less than is 34.2%, but I've changed that to our normal distribution. So instead of saying H is less than, I've got Z is less than 12 minus mu over sigma. And we've got a second piece of data. So Z being greater than 16 minus mu over the deviation is 0.184. Two equations, two unknowns. We should be able to find these unknowns. So on the left-hand side, well, it's a less than, so yes, we want that to be 0.342. The right-hand side is a greater than, so we'd actually like the cumulative to be 0.816. We go to our tables to see what would give us those answers. The left-hand side one, negative 0.41 would give us that answer. So we can play around with that. The right hand side, 0.9 gives us that answer. There's our simultaneous equations. Just a matter of playing with them. Eliminate the mu makes sense. Okay, sigma 3.05, and that would then give us an average of 13.25. So we have our average and our deviation for the cacti, and the biologists are happy. So 16E, 16F, now we can do some good stats.